Okay, in the last video, we had this surface with this boundary curve here, which we were calling C. We had this lovely vector field, and we calculated the work integral for that vector field going once around this curve. We did that as a line integral, and we got negative 4 pi. Now we're going to take advantage of the fact that that line integral, that curve, rather, is the boundary of this surface, and Stokes' theorem says, hey, rather than doing the line integral, we could do this surface integral instead. Okay. So if we're going to do that, I'm going to need to know what curl of f is. So let's calculate that. So curl of f is del crossed with f. Okay. And so that's going to be the symbolic determinant, I, j, k, partial x, partial y, partial z. And then I just write the component functions, y squared, x, z. So let's see. I'm going to get, for the i's, the partial of z with respect to y minus the partial of z with respect to x. That's just 0. Okay. For the j's, partial with respect to z of y squared is 0. Partial with respect to x of z is 0. For the k's, partial of x with respect to x is 1, minus the partial of y squared with respect to y is 2y. Okay. So that's my curl of f. Okay. All right. So then I'm going to get the double integral along s of curl of f dotted with n ds. So I need to describe now how I want to parameterize this surface. Now, since the surface was z equals x squared plus y squared, I'm going to just use x and y as my parameters and use that sort of classic parametrization. So I'm going to switch to integrating over d. That would just be the projection of this onto the xy plane, because that's the domain for this surface, which is then the domain for this parametrization. Okay. All right, so I need to then describe my curl of f in terms of just x and y. That's pretty straightforward because there weren't any z's in that formula. If there had been, I'd replace them with x squared plus y squared. Dotted with. Now, I'm going to replace the unit normal vector with the non-normalized normal vector, okay, because that absorbs the scaling factor, which is the magnitude of the cross product of the two partials that I would get in switching from ds to dA. So if this was oriented downward, I know I want the z component to be negative, and that means that what I'm putting here and here are the partials of z with respect to x and the partials of z with respect to y. Okay. So partial of z with respect to x will just be 2x. Partial of z with respect to y will just be 2y. And then we're integrating that dA. So that's going to be the double integral over d. Let's just work out that dot product. I'm going to get nothing plus nothing. And then negative 1 times 1 minus 2y is going to be minus 1 plus 2y dA. Excellent. Now, since we're integrating over this disk, I think it makes sense to switch at this point to polar coordinates. So that's what I'm going to do. So in polar coordinates, we're going from 0 to 2 pi and from 0 to 2, because this was a disk of radius 2. Remember, this is where x squared plus y squared meets 4. Okay. All right, so it's going to be then negative 1 plus 2y in polar coordinates becomes r sine theta. And then dA becomes r dr d theta. So let's distribute that r. So I've got negative r plus 2r squared sine theta, and it's dr d theta. I think what I'm going to do is I'm actually going to split this up into two integrals, simply because I can see here I'm going to be integrating sine theta from 0 to 2 pi, and that's going to be 0. It's going to drop out. So let me just write it as 0 to 2 pi 0 to 2 negative r dr d theta. That I've still got to do. Okay. Plus integral 0 to 2, 0 to 2 pi. So I'm going to Fubiniize here so that I can integrate with respect to theta first. 2r squared sine theta d theta dr. And now I can just say that's 0 because the integral from 0 to 2 pi of sine theta d theta is just 0. Remember, it's signed area. So we're getting this positive area and this negative area. They totally cancel each other out. Now, if you want to take it a step further and actually find an antiderivative and evaluate it to get 0, you can. But if you're integrating sine theta from 0 to 2 pi, you're allowed to say by inspection that that's 0. Okay. All right, so here, I've got the integral from 0 to 2 pi. This is going to become negative r squared over 2, evaluated between 2 and 0. And then we've got to integrate still d theta. Okay. So that's going to be integral from 0 to 2 pi. 2 squared is 4, so I'll have negative 4 halves, which is negative 2 d theta. And when I integrate a constant, I get that constant times the length of the interval. So that's negative 4 theta. I'm sorry, not negative 4 theta. The length of the interval is 2 pi, not 2 theta. Oh, good grief. So that's negative 4 pi, which makes me feel very good because that's what we got when we did it as a line integral. Okay, I did mention we were going to do this a third way. We are going to. I will explain that in the next video.